In the previous cases, we discussed the extreme scenario where the rent cost is much larger than the inventory waiting cost. So now in another extreme scenario, which is on the contrary, if we have the inventory waiting cost is far larger than the rent cost, then how the problem will be changed. Remember, we have the production line, shipment line, arrival line, and the consumption line. So when we discuss about the inventory waiting cost, we have this shaded area as our focus. Remember, the inventory waiting cost contains two parts. One is the part inside the triangle, and then the transportation time, and then another part inside this triangle. But typically, because the transportation time Tm is not changed, and then the total number of demand dTmax is given, so the inventory waiting cost due to the transportation time remain the same no matter what is your decision or dispatching strategy. So in this end, if we have the condition that the inventory waiting cost is much larger than the rent cost, we only need to pay attention on the area of these triangles. So to make the problem simpler, we make an assumption that is the holding cost now is proportional to the shaded area on the demand side. So that means, so we will not consider the production side. Let's see if this is A, this is B, and we do not consider the holding cost at A, or the holding cost at A is the same as that in B. So this assumption is necessary because although we know the demand curve, we do not guarantee that the production curve is the same as the demand curve. So to really focus on the triangle area, we need to make the analysis consistent on both sides. So we either ignore the side on A, or we consider the triangles on A are the same as the triangles at B to simplify our analysis. So under this assumption, we just need to focus on one side, which is the consumption side. So all the holding costs are just the area within these triangles. So given we have a finite time cumulative items, similarly, we know that demand at the end of the planning horizon is dTmax. So the question is, under a certain number of transportation, the number of shipments is equals to n, then how should we find the dispatch schedule or the load size? Now let's see how should we optimize the decision of dispatching. First, let's consider the simplest case when we only need one dispatch. So this case is kind of trivial. So we know this demand curve. So because we only need one dispatch, then our dispatch has to be at the beginning, and then order should satisfy the entire demand. And then we can calculate the shaded area, which is our objective. So the holding cost will be the integral from 0 to Tmax, dTmax minus dt, which is a physical meaning as the integral as the triangle. Okay, so the optimum decision, actually our dispatch decision is 0. This is the only decision, definitely this is optimal. And then the total cost will be the holding cost plus the transportation cost. Because we have only one dispatch, so we have CF times 1. Okay, and the total cost is their summation. So this is a case when n equals to 1. Now let's see a more complicated case when n equals to 2. So when n equals to 2, the problem is no longer trivial. So we need to decide one dispatch point in the middle. Definitely 0 is our dispatch point. So our dispatch will result in this arrival curve. Okay, so this point will be t1. So let's see what is the holding cost. So we have this holding cost. This will be two integrals. First integral from 0 to t1, and then dt1 minus dt. And then the second integral will be the second triangle from t1 to t max. Then it will be the dt max minus dt. Okay, so notice that this is a function of t1. Yeah, so we need to find out the optimum decision for t1. So this is a continuous function. The first step we can do is to find out the first order condition. Find out the first order condition, we calculate the derivative. Notice that this is a derivative for integrals. To calculate the derivative of the integrals, we will just review our Leibniz integral rule. So the Leibniz integral rule is we will want to calculate the derivative of an integral. The integral may have upper bound and lower bound with function inside of two variables. One is a variable you take the derivative, and another one is a variable inside the integral. So this can be calculated based on three terms. So it equals to take a derivative of the upper bound and then plug in the upper bound inside to replace d. And then minus take the derivative of the lower bound and then plug in t with the lower bound. And then we take the derivative inside. Okay, with this Leibniz rule, then we can calculate the derivative of these two terms separately. Okay, we call the first term, let's see, term 1, and then the second term is term 2. So let's calculate them one by one. So for term 1, we need to calculate the derivative over t1 from 0 to t1 dt1 minus dt small dt. So based on the Leibniz rules, we take the derivative of the upper bound and then plug in the upper bound inside t. And then minus the lower bound derivative times we plug in t with the lower bound. And then plus the derivative, the partial derivative inside. Okay, and then interestingly, this is 0, dt1 and dt1 are cancelled, and then this is 0 because the derivative of 0 is also 0. So the only term is the last one, and then the last one is very easy to calculate because the partial derivative of this function is just the d prime dt1 dt, because the partial derivative of dt is 0. And then we can get this out. Okay, so this is our term 1. So let's see our term 2. So we need to calculate, given t1 to t max. So here, similarly, we use the Leibniz rule. The derivative of the upper bound, and then plug inside, minus the derivative of the lower bound, plug it inside, and then plus the partial derivative. So interestingly, so this is 0, because the t max is a constant, the derivative is 0. Then the second term, the derivative of t1 is 1. So we have this, the second term. And then the third term, because the partial derivative over t1 for the integrand is 0, because there's no t1 inside, so the third term is 0. So then we have the results for the term 2, just minus. Okay, so we have two terms. So we can have the first order condition. We set this to be 0. Then this can give us the condition, optimality condition, is the derivative of dt1 equals to t1. Okay, so this is interesting results. So this first order condition have a physical meaning. Remember, we have our curve. So if this is t1, this is tmax, and this is 0. So the physical meaning for this expression, dt1 actually is the tangent line. This is dt1, d prime t1. And then on the right hand side, this is the gradient of this line. Because this is dt max, this is dt1, and then this is t1. Okay, so the physical meaning of the first order condition is the gradient of the line connecting the two triangles is the same as the gradient of the tangent line, same as the gradient at t1. So how should we utilize this first order condition and its physical meaning? So that means if we have demand curve given, and then we will search a point t1 gradually from the smaller value to a larger value until tmax. So if you find out one value, and then you will have this gradient, and then because of the equilibrium condition, we know that the gradient connecting two triangles should be the same as the gradient passing through t1. So we just find the dispatch at t1 here. Load is determined. Then we can have our destination at this point. So if this point is the same as tmax, then we create a optimum solution. So in this case, we should increase t1. Or if we have another case, this point is t1, and then we have this gradient, then we know the first dispatch is 0, so we create this line the same as this gradient, and then we can find the load. See another case. Then your T1 have a tangent line with a gradient, and then from physical meaning of the first order condition, we need to draw a similar line, parallel line, and then the load should be determined here. Okay, you can see definitely the point is over Tmax. So that means your T1 is too large, so you should go left. So finally, you can find out a good T1, the point I exactly matches. Now we can extend to a general case when n equals to any number. So for any shipments, we know Tmax. So we can find out T1, and then starting from T1, so this is a subproblem when n equals to 2. So all the conditions are satisfied, so the gradient will be the same as this gradient if you want to achieve the optimum. Okay, so in another way, so that means we can generate the optimum solution based on the selection of T1. Let's say we choose T1 at this point. So based on the condition, we have a gradient, and then we draw a parallel line, and then find out the load, so we can find the next time. Similarly, we can find the gradient, draw a parallel line, and then find the next T3. And then keep doing this. This is T4. Until finally you reach Tmax. Then you generate the optimum solution given a certain number of shipments n. So finally, your total cost should be CFN, which is our transportation cost, plus the total holding cost. Unit to time, the unit inventory waiting cost. Yeah, here we'll forget. Here's the inventory waiting cost. So in summary, for the inventory waiting cost is much larger than the rent cost. We create a method, searching method, which we call it a shooting method. So that means for a certain amount of shipments n, we need to find the T1. This is our decision. After we determine this decision, all the rest dispatching strategies is generated based on the gradient method or the shooting method. The gradient parallel, gradient parallel, gradient parallel until it reaches the Tmax. And then you can calculate this total transportation cost and the total holding cost. So after you have all those total cost for each n, then you just take the minimum of this n costs.